I'm very happy to be back here as an intern in 2005, and I see that a lot of things have changed, new buildings, new people, and I'm actually happy to be here because I needed a new T-shirt. All my old ones are battered, and a little interesting thing that happened after my internship here was I went to intern at Microsoft, and the contrast was very interesting. People here were saying, it was 2005, I remember the situation, was saying, oh my God, Microsoft is after us. They're so big, they have so much money, every company that they've gone after, they're dead, we're doomed. And then I go to Microsoft, oh my God, we're not Google, and they have so much money and they're in front of us. So it's interesting to see a few years later, Google is still standing and Microsoft still fighting. So we'll see what happens. So today I'm going to talk about my thesis work, and I'll first start by introducing the field in general of nonparametric Bayesian methods. It's probably unfamiliar to a lot of you, and then I'll hone in on specifically what I did. From even further back, if you want to say what is this field, it's the intersection of computer science and statistics, which would be maybe a good definition of machine learning in general. But in particular, I'd like to emphasize the differences between the two fields. One is computer science. One thing that has done really well with the kind of thing that students in computer science get excited about first is all these data structures, lists and trees and all the algorithms on them. And what statistics has been really good with is how to make a good decision with poor data, with uncertain, noisy data. How do you do that? And but what statistics has been working on is mostly data that is d-dimensional vector, so a random variable that is a real vector, not complex data structures like trees and all that. So we're trying to bridge that gap with these methods. So nonparametric Bayesian methods, to introduce them, I'll start with an example that is maybe the poster child for this domain. And the example is clustering. You have a number of data points, and let's say a simple clustering problem where you want to cluster points into into roughly Gaussian bumps. So here you have a number of unknowns, which are theta, the cluster centers, and then maybe you want also to evaluate the relative size of the different clusters if you don't think they have all equal size. So you have pi is the proportion of each cluster. And the goal is to estimate that from data. So to complete the model, you need an observation probability, which is, let me grab this laser. Observation probability xi is drawn from a normal centered at the particular cluster center that item I belongs to, and with, say here, a fixed covariance. So it's, oh, it's just because this is two-dimensional, and d is the number of clusters here. Okay, maybe d should mean dimension, and so right. That's. So if you take a Bayesian approach to this problem, you will say, all right, I don't know these parameters. I have uncertainty about them, so I will say that I have a probability, a prior probability over these parameters. And now the goal is to recover these parameters. Really, you're doing inference. Given the data, use Bayes' rule to recover a posterior probability over your parameters. So what, I'll try to give a picture representation. There's really two things going on here. There's the model, which is the particular assumptions you made, the number of clusters, and the particular shape of the likelihood, the observation model. And then there's the prior. On that model and all the space of possible ways that data could be generated, you have this prior. And these two things do kind of the same thing. They tend to restrict the ways in which you can explain how data is generated. And one of them is just a hard constraint. You can be anywhere here, I don't care, but nowhere else. And the prior is a more smooth constraint. I'd rather you be here, but if the data is really says you're here, then okay, you can go there. And you can view nonparametric Bayesian methods in two different ways. The traditional definition is it's doing Bayesian inference, but with an infinite number of parameters. That's one way to see it. But the other way to see it is try to diminish the model. Try to get rid of the model as much as possible. You can never get rid of it completely. So here, the number of clusters is something that you might want to get rid of because that's a hard constraint, and put all the work into the prior to allow you to go to what would be different models. So one way to do this is by using the Dirichlet process. Dirichlet process is a random measure. I'll explain more in detail later what a random measure is. But you can imagine on some space, here the real line, a number of sticks with total mass that sums to 1. And these sticks are random, so their location and the size of the sticks is random. And they have a particular distribution that is the Dirichlet process distribution, and they sum to 1. So therefore, this little picket fence here is a probability distribution because it sums to 1, and it's a random probability distribution. So what can you do with something like that? How do you help solve the clustering problem from before? So imagine you have a number of data points called y, and one thing you can do is draw from this distribution. Once you know the picket fence, draw data points from that distribution independently. Because you have sticks, you have a non-zero probability of falling in the same group as the previous data point, and therefore data points will form groups, and this patterns of ones will be a clustering of your data. The advantage is that here the number of clusters is random, that as you grow your data, you will discover more and more clusters, and you have a coherent probabilistic model over any number of data points. So I won't go through the whole history of the Dirichlet process, but just want to highlight one part, which is Escobar and West, who realized after this is a definition and more understanding of the Dirichlet process, and then finally it was understood that really the Dirichlet process it's a very good tool to do just that, to get a clustering, a random clustering. And here's the kinds of applications that have cropped up that use the Dirichlet process in some way or another. And for instance, things like protein folding, this is the case where using Dirichlet processes, you can do density estimation for the angles between two elements of a protein. And that's something that is very important to be able to do the protein folding, because it factors in the cost function that you need to optimize to try to find what is the best possible configuration of the protein. And so why is this so important to have a random number of clusters? After all, you could say, well, you could use something like k-means and have a fixed number of clusters. And maybe if you're not happy with that number, or try a few numbers around there and do a little search. That wouldn't be as elegant, but maybe that would work. But think of things like grammars. If you want to discover a grammar, you will need not just to guess what the number of possible labels for words or phrases are, but also how many rules there are, how many sublabels there are for each particular label. So now you have lots and lots of questions of the same type. How many, what is K and K means, that are all interrelated, and there's no way you can search over that space. So in these cases where you have more complex models, you gain a lot by going this route. So to summarize, this is Bayes' rule, and this is really what we're using. The likelihood, the prior, and the posterior is just the product of the two. So you have an important part, which is what is this prior. And for parametric models, where theta is just a random vector in RD or R2D, then this is something relatively simple. But in the case of non-parametric models, you will replace theta by G, and G is a stochastic process. So something like the Dirichlet process is a more complex object than just this theta. Oops. And some of the examples of things that you can build out of Dirichlet processes are things like directed trees of unbounded depth and fan-out. So things like grammars are a little bit like this thing. Partitions, we've talked about that. Binary infinite matrices, we will talk about this. And then distributions on distributions, that's, for instance, the Dirichlet process, one of those. All right, so where I come in this story is in two places. So one is I worked on inference algorithms for the Dirichlet process. But also I tried to go to cousins of the Dirichlet process. You've seen all these applications of the Dirichlet process that's really just with the Dirichlet process and a few variants that are at the core. So maybe there are things that we can do with other types of processes, and probability theory has come up with a bunch of interesting processes that maybe we can use the properties of. So here's one, the beta process. It looks the same on my picture, but it's not. It's slightly different. You have a bunch of sticks, also locations at are random and heights are random, but it doesn't sum to 1. And the sticks, though, are between 0 and 1. And what can you do with something like this? And I'll explain more in detail what exactly is this beta process. You can do the same thing. You sample points, but instead of having a clustering, you will have a factor representation. So what do I mean by that? For each, think of these as features, and with probability equal to the height of that stick, I will have or not that feature. You get something like this. So if you're Amazon, maybe your clients are not to be distinguished into a bunch of groups that are separate, where you're pretty much the same when you're in the same group, and completely different if you're not in the same group, which is what clustering is about. But maybe between this client and this client, they share the fact that they like cooking, but also this guy likes electronics, and this guy too, etc. So that's a richer structure that you can't really get with, yes?
To understand this relative to the Dirichlet process. So here you are allowing yourself, you can have multiple of these. So the other one is one of.
Right.
Here you can have any of, but with some probability given by the height.
Yes, yes.
That stick.
Yes. So you can view this as you can belong to several groups at the same time, rather than just one. Mm-hmm. Or you can think of it as features and say, I'm represented by the sum of my features. Mm-hmm. To introduce what the beta process is, I'll need to introduce a more general family of things from probability theory called Levy processes. That's going to include the beta process, and it's going to include other things. And by taking this higher level point of view, then we'll be able to see, okay, what is common to the beta process to this other thing called the gamma process, and get a more general understanding of these, and do algorithms that are common to all. So first, before I introduce Levy processes, I introduce the this is an example of Levy process that you're probably familiar with, the Poisson process. And it's a very important example. And because from the Poisson process, we will construct Levy processes later on. So I will go through the Poisson process, make sure we all understand. So here is some intensity function. And the Poisson process is the process that samples points independently along the line. That is, so the number of points that fall into an interval is Poisson distributed, hence the name. And with what parameter of the Poisson distribution is the integral of this intensity. So you can think of the intensity as the amount of clouds that you have above ground, and these points are the number of raindrops that you get. So let's see. So an important property of the Poisson process is that if you have two intervals that are disjoint, then the number of points that fall into one or the other is independent. So if you're struck by lightning, that doesn't make it more or less likely that someone next to you will be struck by lightning too. One thing we'll do is we'll talk about measures. So here we can view this set of points as a set of points, or you can view this as a measure. So what is a measure? A measure is a function that gives mass to sets. You give it, for instance, the set A, and it tells you 4, because the mass of A is the number of points that are in here. Okay? So measures can be continuous. For instance, this intensity density F, you can turn it into a measure by calling it capital F. And what is capital F of A? It's the integral of little f, so the amount of mass that little f gives to the set A. So using this notation of this terminology of measures, you can express the fact that the number of points here is Poisson distributed with this much mass in a slightly more compact way by saying that this measure n, which measures the number of points in a set, applied to the set A, is Poisson distributed with parameter f, which is the measure associated with little f, applied to capital A. Any question here? Yes.
So big FA is the integral.
Sorry, say that again.
Is this big f of A is this
Big,
integral?
that's right. I should have written that. So big F of A is. Let me actually IA. Yeah. So F of A, that's this thing, over A of f of x dx. Okay, I'm done. So this is an example of a Poisson process in 2 dimensions. It works the same, but just to have a picture in mind of what it looks like. So I've talked about discrete measures, in particular, the sum of points that fall in the set. To be a little more precise, I'll be more clear about what this measure looks like. We'll draw it as a stick of size 1 whenever there is a point here. So we can represent the Poisson process this way. So let's call the space omega. So maybe the real line here. And little omega I is the red color okay? All right. So if not, I'll change the lights maybe. So little omega I is the position of these atoms, and so this point is little omega I1, all right? And so the mass that falls into A is the sum of 1 for all the points that are in A. Okay, all right. This is easily generalized to different weights than just 1, and the weights that is associated to the set A is the sum of the weights of the atoms that are here. So I'm going slowly here, but actually we're very close to being able to define Levy processes using this. So Levy processes are discrete measures like this that have the property, just like the Poisson process, that the mass that falls into A and the mass that falls to B, if they are disjoint, is independent. Okay, and that's the definition. And now we'll give a more constructive way to build them. There's something that is associated with the Levy process by theorem. It's called the Levy measure. The Levy measure is, you can imagine something like this. It's a measure over the space, omega, on which you want to define your measure, your random measure, plus an extra dimension. And this extra dimension is going to be the dimension in which the weights of the points will be drawn. So this measure nu, the Levy measure, I've drawn it Lebesgue measure across something here, is just to make it convenient to draw, but it can be more general measure. And what you do with this, you draw a Poisson process with the Levy measure as base measure, get a bunch of points, and now you look at this sideways, and you have a random measure. You make the sticks that go all the way to omega. And if you look at it, you have the same picture as we had before. Okay, so the mass that falls into A is the weight of the sticks that fall into here. So a little detail here that I mentioned is here, because it's a Poisson process, you will never have twice a point. If you draw another set of points, it won't never twice come at the same position. If you do want atoms that have a fixed position but just random weight, you can just add that in also. Then you can
mention what's the third dimension?
This height.
Yes.
That's the intensity of the Levy measure. That's right. So it's the same picture as this one.
Okay.
Yes. Same picture. So now we're ready to define the beta process, and all we need by theorem to define the beta process is what is its Levy measure, and also if it has fixed atoms, what is the distribution of those fixed atoms. So here it is, and I'm not sure you want to parse that, but so the Levy measure, it's a measure on omega, or the space on which we want to define this measure, and p, the mass of these atoms. And if you look at this, if you're familiar with the beta distribution, this looks like a degenerate beta distribution. So hence the name beta process. Also, the fixed atoms, if you have any, they are beta distributed. So again, that's the name. What does that look like? Looks like this. So this is the intensity of so this is the Levy measure. Again, I've drawn, using a uniform base measure B0, which is one of the parameters of the beta process, but it could be more general. Yes?
So in the case of fixed atoms, I'm going to make B0 to be full concentrated, just where those atoms are going to be non-gain.
That's right. Okay. Yes. So B0 can be mixed, continuous, and discrete, and the continuous part is going to look like this, where you have a Levy measure associated with it. And then the discrete part, you just take that separately, and you have a bunch of beta distributed atoms at fixed location. And in particular, this Levy measure is special. It goes to infinity here, and it's not even integrable. So what that means is that you're going to have an infinite number of points here. But that's okay, because when you compute how much mass there is in a particular set, the mass is still going to sum to something finite, because most of these atoms are close to 0. By the way, the Dirichlet process is not a Levy process, but almost up to a random scale. And it has, a similar behavior. It has an infinite number of little sticks. When I drew it, I had a finite number, but really it has
So the
infinitely many.
summability of that is a theorem that it's not totally obvious that these would be summed.
Right, right. Yes, it's a theorem. It's really the expected mass contributed by a particular set in that omega across p space is the integral of that. So it's integral of this Levy measure, but times x times p, because you need to weight by by how much weight is going to be given to each point. So if you do that, if you multiply this by p, then this becomes integrable, and therefore you have finite mass.
So when you originally drew the Dirichlet process, I was confused because I thought you meant that only those sticks had any probability and all the other real numbers had none. But what you're saying now is that all the real numbers have a small stick, you just didn't draw the ones that are nearly zero?
No, I'm saying you're right on both ways. So it is true that the Dirichlet infinite number of points, that's still much less than the uncountably infinite number of points that are on the real line. So most points, in some sense, don't have mass. And so same thing here. Yes, yes. So what you do with the beta process, you do this, which is what I sketched earlier. For each stick, you will sample a 0, 1 indicator variable to decide whether you have or not this feature. Take this terminology. So here, if I draw a bunch of points, here's the kinds of patterns that I see, and I see that some features are shared a lot, some features are not shared a lot, etc. So this pattern of points, you could, so if you wanted to do this algorithmically, to draw this number of points, you have a little problem, is that the way I've defined it, you need to sample B first, and then given B, sample all these guys. But you can't sample B completely because this is an infinite object, you have an infinite list. So instead, what you can do is ask, what is the distribution of x1 marginally if I marginalize this object? And now, what is the distribution of x2 given x1? And again, marginalizing this object. And you can do that, and you get this thing called the Indian buffet process, which was actually invented before we discovered the link with the beta process. So history didn't go the way I say. So you have the metaphor goes as follows. You have an infinite, so you have a big restaurant with an infinite number of dishes. And customers come in and try a few dishes. And that's going to be which features they have. The first customer is going to try a few dishes. I'll say more precisely with what distribution. Then customer 2 is going to try a few dishes, make a decision whether to try the dishes that have been tried already, and then maybe add some more new dishes that no one has tried before, etc. So the rule is that customer n+1 tries each particular dish with probability proportional to the number of people who have tried it before, so the rich get richer. And also will try a Poisson distributed number of dishes, of new dishes that no one has seen before. And why a Poisson number? That's related to the fact that the Levy process is constructed from a Poisson process. All right, so what can you do now with this? That's an example of what it looks like. And I've said this is the same thing as the bunch of points that I showed sampled from the beta process. But it doesn't look the same. It's just because I've ordered the columns in the order in which features are discovered. So it looks biased like this. But if I randomize the order of the columns, then it'll look the same.
Oh, I was thinking about randomizing the order of the rows. But, I guess.
OK, so there are two things you can do. What is an important property that maybe you're thinking about is exchangeability, which is that if you permute the rows here, the distribution is the same. and it doesn't look that way because I've ordered it in this particularly funny way. But if you shuffled the order of the columns, then it would be more clear that the order of the rows is actually exchangeable. That's actually the exchangeability is actually an important property, because when you have exchangeability by Definiti's theorem, you know that there exists some object that is behind this, and maybe if I have more time at the end, I'll talk about that. And that's how we knew that there must be something, and now the game is to find what is this object. Turns out it's the beta process. So here's a set of examples of applications of the beta process or Indian buffet process, and so this is more recent than the Dirichlet process, so it has less applications, but growing there. And more specifically, what you get out of the connection between the beta process and the Indian buffet process is this set of things, size bias construction, which is a way to build the beta process in the order in which the features are discovered by the Indian buffet process, so a kind of merge of the two. A way to sample the beta processes that used in statistics, and they have algorithms to do that, but that's a much simpler way to do it. And then hierarchies of beta processes, we'll talk about that, and new kinds of models of data. So why new models of data, just before I go into hierarchies? Because when you know about the Indian buffet process and it's exchangeable, it's pretty hard to come up with a new model that now would talk about counts, where you can observe a feature more than once for a particular object. You have to reinvent another system of rules, like a new kind of restaurant, and make sure that it's exchangeable. It's pretty hard. But if you go the other way, you start from a process and you have something that's drawn independently from it, you know that it's necessarily going to be exchangeable. So whatever you do is going to be exchangeable. So it's much easier to go from this higher level and go the other way than history went. So hierarchies of beta processes. I need to hurry up now. So what a hierarchy of beta processes is, and before I start, I should say, why did we even think of doing something weird like this? Because Dirichlet processes also, hierarchies have been defined for them, and they have been very, very useful. And we'll see some uses of that, but already at the outset, just by analogy, we know that doing hierarchies is going to be important. So hierarchy of beta processes is you have a beta process B whose base measure is drawn itself from a beta process. What that means is that the top level beta process is going to have these bunch of atoms at random locations. And this one now has a base measure that is entirely discrete, and therefore it will have atoms at exactly the same locations, but they'll be beta distributed with mean the height of the stick. So it'll be a kind of fuzzed up version of this top level one. And then you can draw samples from this thing, for instance. Yeah, that's just in math what I've just said. So what kinds of things could you think of doing? For instance, if you have a bunch of documents that are represented as the set of words that they contain, and each, you have a 1 if you have a particular word, so just the binary vector. What you want to do is to estimate what is the probability of each particular word in the set of documents. So really you want to go after what is the particular beta process that this thing is drawn from. If you have several categories and you want to estimate the probability of each word in each category, you could do this independently and try to estimate, maybe with Laplace smoothing or something, these probabilities, but really they are related. If the is very common in this category, in some new category that you've never seen before, it's likely to be also very, very common. And that's important to find the relative size of these probabilities very accurately if you want to do classification. If you have a new document that you want to, now you want to say, what is this probability if I assume that it comes from sports or from science or from politics, and you do, that's naive Bayes classification, and you want to recover what the most likely category is, then you want to know these probabilities very precisely. So you want, if there is information to be shared between them, you want to be able to share them. And that's something that you could do with hierarchies of better processes, where you have a random base measure that is, a random center around which each of these is drawn. So each of these is a fuzzed up version of the top level one. So if you use this compared to Laplace smoothing, so Laplace smoothing is a method where to estimate these probabilities, you assume that you have seen this word before in this category at least once, and you have not seen it at least once, to make sure that when you estimate the probability just by the empirical counts or empirical proportion of times that you've seen this particular word, it doesn't go to 0, which is doesn't make sense. So if you compare the probability that is given to unseen document just on one category, if you have data from several related categories, then the probability is higher if you are, so the probability given to unseen data is higher for the hierarchy of better processes. And that's really expected because Laplace smoothing is not looking at other categories, whereas this is using data from other categories. So there must be some information that is drawn. And if you are better at predicting what documents will look like in a particular category, you should be able to be better at classifying what is the right category for a particular document.
Excuse me?
Yes?
How many parameters did you have to estimate or put in?
So there's several answers to your question. One is what is the number of hyperparameters? If you're a Bayesian, if you have, you put probabilities over parameters, you don't fix them. But there's always one or two parameters at the top that you need to fix. And that's what is the mass of the base measure at the top level? What is the concentration parameter at the two levels of the hierarchy? So that's really 3 parameters. And now the other way to answer your question is, how many things are you trying to estimate? And how many things do you have probability over? That's all the topic-specific feature probability for each word, for each category. So that's a lot of features. But observe that here, because we're talking about Levy processes, what happens in a set that is in sets that are disjoint is independent. Therefore, inference on that particular feature is unrelated to inference in that particular feature. So you can run inference separately on a hierarchy for this feature and then a hierarchy for this feature, etc. I don't know if I answered your question.
Well, the first answer was more on the line I was aiming at. So you optimized for these 3 parameters by some criteria?
No, so what I do is that so 2 of these parameters I can set using, by matching expectations of a flat model where I have just one level instead of 2 levels here. If I assume I have 1 level, then I can say for a particular value of these 2 parameters, how many features do I expect to see, and how many distinct features do I expect to see. And so that's related to what this Indian buffet process matrix looks like. And using these 2 parameters, I can match that to my data. And then the last parameter, I can fix that. I just 1 parameter now, so I can go over a few values and use cross-validation to choose that particular value.
So
Yes.
another baseline.
Sorry, up or
The next one?
the next one? Yes.
So another baseline here is instead of taking the Laplace smoothings independently of each one of the matrices, is using all of them. And I would expect it would be higher than the blue, and the question is how. So how much do you gain? How much of the red gain is because you have a hierarchy of beta processes, and how much is because you share? You basically have more data because you share more classes.
I don't know. I have to, that would be a good experience to do. I suspect if you just merge all the classes together, you pretend that you have just data from one class, at some point it's going to hurt. If you have too many classes, now it's going to look like, some average of all the classes, not something very specific. Whereas here, if you use a hierarchy and you add more and more and more other classes, it's not going to make your estimate go towards the average of all the classes. It's going to converge to something close to your estimate if you had just one class, but just slanted towards the average of all the classes. Yes.
So let me see. Try to understand this experiment a little bit. So you have the set of classes is not given. Is you basically you're inferring what the classes are.
No, the set of classes is given. So you're probably thinking of using nonparametric Bayesian methods in the way that the Dirichlet process is used, where you have really a clustering problem, and you want to discover which documents belong to which class.
So if we go back to the previous picture,
Yes.
all right. So when I do this, the choice of so you do not have the number of classes. So the choice of the hierarchy, the sort of the fan out of that hierarchy
Right.
is predefined.
Yes, exactly.
You don't have another
Yes.
process that speaks out.
No,
I
no.
have some number. There.
Right, yes,
Okay,
yes.
that's what
So
my question.
it's a much less ambitious application than if you wanted to do what you're saying.
Okay.
Yes.
I just trying to.
Right. And so these types of processes are motivated by this, but also about the type,
Okay.
by the type of application that you're thinking. But here, so why did I start in this direction? Because I want to make sure that whatever I do is really, really scalable, which is a question right now on nonparametric Bayesian methods. How much does it scale? And the difficulty is that really it's attacking really hard problems, like nested clustering problems that are just intrinsically hard. So trying to go from the other side, try to find what is the simplest thing that you can do to really scale, and try to make it more complex. That's what this is about. Okay, so if you use so this is an experiment on the 20 news group data set where you want to classify into one of, I don't remember, like 10, 12 categories, and I compare hierarchies of beta processes to naive Bayes. Here, the features that I used is all the words in the document. Yes, you have a question?
Excuse me. So if you compare this to hierarchical Dirichlet process, what will?
I don't know. So you are thinking of using the hierarchy of Dirichlet process where you have again you observe the different classes. But instead of observing the represented document as a binary vector of the words that it contains, it would be the multinomial vector of the counts of each word, and then you have a Dirichlet process over that. I haven't tried, but that would be interesting. And just so the words that are used here is just cut at every space. So you have a lot of junk, a lot of features that are extremely rare. And that's why it's particularly important to smooth them correctly. Otherwise, they're just going to take over the estimate. And the naive Bayes here is instead of trying to do, so this is using the method I've described with using cross-validation, and this is looking for all the possible parameters for naive Bayes on the test set and trying to find what is the best number, and that's what you get. But that's really a case where you have a lot of rare features, and that's really the kind of places where this kind of method shines. So inference, I've already talked about that. You can, because you have independence on disjoint sets, you can do inference separately on each of the features. So computationally, it's very fast. And all right, so now I'll talk a little bit about variance, and maybe if there are questions, this is a good time. Otherwise, things that you can think of doing. Yes, question.
Well, it's not that you lack generality, but if you go that far, I wonder why you have the p to the minus 1 here and 1 minus p to the c minus 1 there. Why not go all the way and add another constant?
Another constant?
Meaning, why is the p to the minus 1 sacred? It won't be p to the minus gamma.
It's, I think here it wouldn't be that big a difference in the particular application that I'm showing. For applications where you want to do something more like clustering, where you want to guess the number of features, which is the more typical application, then your model and this one are saying slightly different things. Your model is saying, because now your Levy measure becomes integrable, you're saying there's a finite number of features, and I just don't know, how many and what they are. But at some point, if I see more and more data, I'm going to know what the features are. Whereas here, it's saying there's an infinite number of features, and the more data I see, the more rare features I will discover. So it's slightly different assumption, but you could think of using that too.
It's beyond the finite infinite. I mean, you could have there p to the minus 1.5, and still, if you multiply by p, it's integrable. Or you could have p to the minus half, which is.
That would be anything greater than -1 would be integrable, because it would be the base measure would not be integrable by itself, but what counts is the base measure multiplied by p. So you have so then that would be integrable. All right, so the kinds of things that you would want also, I'll go fast here. Let's see, how much time do I have? Not much, so I'll go fast. Another example, won't really go into details, but you can think instead of using a beta process, you can use a gamma process. And we've derived a lot of things that we've derived for the beta process, we've derived them also for the gamma process, things like the size bias construction and hierarchies and all that. So you can do that also. And gamma processes are an example of Levy process. And that's why going to Levy processes, makes it obvious what is the relationship between the two. It makes it much easier to go from one to the other. It's not exactly the same, but it guides you a lot. And what you can do with a gamma process is have, given this parameter, you observe a Poisson number of observations from that with parameter this much. And now you have something that's even more general than the Indian buffet process, these random binary matrices, because you have numbers here. So an example of image classification, really, in this example, I'm just going back to the text case. I transformed this image into a bunch of words, quote unquote, by taking CIF descriptors, which is something standard in vision, doing vector quantization to get a bunch of visual words, and then describe the image as the binary vector of words that it contains, or vector of counts of words that it contains. You can also, so I've described the gamma process. You can also use the beta process with a geometric distribution instead of Bernoulli distribution, and that's also a way to get counts, and that has other properties because the geometric is the shape and the Poisson is more like little bell curve. So depending on your data, one might be better than the other. So that's gamma process again. This is equivalent to, this is what is behind a model that has been proposed at NIPS last year. I won't go into this. And some results on image classification. This is compared to support vector machines, so it does pretty poorly on the same set of features. And we've tried to reproduce as best as we could the features from that paper that's the Zepnik 2006. But really the one thing that is not shown in that graph is what is the speed at which this computation is done. And this we're talking about 3 minutes, whereas here this is a 1 versus all support vector machine. So on things like, this is on the 15 scenes categories, you have to do 15 times the support vector machine on all the data. And for things like the Caltech 101 data set, then you have to do 101 times. Also, the cost here is related to the number. I'm saying related. I'm reluctant to give a precise complexity because the packages for SVM have made a lot of progress. I'm not sure what the latest number is, but it can be just linear, and these methods are linear, basically the same cost within constant factor of naive Bayes. It's pretty fast. So this is pretty expensive. And yes?
So to make sure I understand, so you basically, estimated those probabilities, and now you're just doing naive Bayes classification, extended naive
Yes,
Bayes.
yes, that's right. So seeing that, we said, okay, well, let's go to a data set where there's really so many classes and so much data that SVM can't compete, and see whether we can do anything. And that data set is the 80 million tiny images data set from Toralba, Ferguson, Freeman. It's a very interesting data set. They've collected 80 million images from the web from various sources and reduced them to size 32 by 32. And they have an argument, and you can tell from yourself that even 32 by 32, which is really, really small, you can tell a lot of stuff that's going on in the image. And that makes also it more amenable to like putting it on one computer. But now you have, so how did they do this? They took the WordNet database of words in English, took all the words that were concrete, and sent that to search engines. So now you have lots of categories associated to all these words. So that's like 50,000 categories or something, and it's 80 million images. So these are examples. And the WordNet, so before we go into classification, we can't really think of classifying and be judged on exactly recovering a beauty consultant from just looking at the face of that person. So instead, we use the WordNet hierarchy of hypernyms, and we score a guess by how many nodes in the hierarchy do we get right, except the root. And we can also think of using this hierarchy to have a hierarchy of Levy processes, so beta or gamma processes, that follows also this hierarchy, because it is expected that images will be similar visually, maybe, but at least a priori, if they are from related categories. And that's roughly visible in this picture, as drawn from their website. It's a very interesting picture. That's all of this data set compiled into one big poster. And the position of, so each dot here is the average of one category. And the position is related to, so things that are close in the tree are close together on the poster. So you can see that plants are here. So there's some hint of visual similarity, at least that's associated to semantic similarity. So we're going to use very simple color features based on that poster. We see that color at least is related. And we would like to use more advanced features, but for now that's all we're using. We just cut the HSV color space in some way. And the scores that we get, so if you were to guess one of the leaves at random, that's the kind of score that you would get. No, I don't want to back up now. It's not a good time. Whoop. And so now you can compare several things. Laplace smoothing with a gamma Poisson model. to a flat hierarchy of, so flat, what I call flat hierarchy is the same as for the text before, just one level. And then using the WordNet hierarchy, so you see an improvement from one to the other. And then the same thing, but using beta geometric model, and you see that beta geometric must be a better model of what this data is. And that's some analysis of an example, but I'll just leave it at that. And I think I'm late, so thank you very much.
I missed it. What is a hypermean?
The
score you use?
Oh, yeah. So imagine the tree of all these hypernyms, so like generalization of words. And you have this tree whose leaves are all these categories from which you have data. And now the score is if this image, I say it's actually from this category, then I find their common ancestor in the tree, and my score is how many nodes in the tree do I have in common. So if I'm in the same category, all the nodes will be common. So the higher is the better.
Yeah. How deep was the hierarchy?
The thing is, it varies depending on this. It's not a fixed size hierarchy. So like that's one example was this thing. Yes. So these scores are, like you're not very deep, but this is a very difficult data set and using very, very simple features.
So for image classification example, which data set did you exactly use? The 13 scenes or Caltech?
The 15 scenes.
15
Yeah,
scenes.
15
Okay.
scenes, yeah.
What
Yes.
did you do with these HSV features again? Are you making a feature for every pixel in the image, or the average color? Or what?
So something like that, except I don't want to have. I want to have some kind of features that correspond roughly to visual similarity. So here, all the black part, I say that's one feature because I'm not able to distinguish between this black and this black, even though.
What are you applying it to? Every pixel, or the average of the image, or something else?
I do a count. So think of all these as bins, and I count how many pixels fall into that bin. So I have each image is 120 for the number of colors here, dimensional vector.
Thank you.